Hello, college biology. This is the third and final chapter of lipids, glycerides. And glycerides are molecules that our cells make with fatty acids in order to use those fatty acids. So let's take a look. All glycerides start with a glycerol, which is a 3-carbon compound, and each carbon has a hydroxide group. So this is our glycerol. And a glyceride is simply a glycerol that has had fatty acids attached to it, linked to it. So right here, we're in the process of making a glyceride because we have our glycerol here. We've got a fatty acid here. They undergo a condensation reaction where the hydrogen here and the hydroxide group here are removed. They form water, and then this carbon will bond to this oxygen to form our glyceride. Now we have different types of glycerides. We have monoglycerides, which is simply one fatty acid connected to the glycerol. We have triglycerides, which have 3 fatty acids connected to the glycerol. And triglycerides have some significance. They are the cell's most common fat molecule for the purpose of energy storage. So this is a long-term energy storage molecule. Our cells can make glucose out of these long carbon chains, and so when we have more energy than we need, we produce these triglycerides for long-term storage, and then we chop them up later to get energy out of them. So that's our triglycerides. Now, the interesting phospholipids, spoiler alert. The interesting glycerides, in my opinion, are the diglycerides, and so those simply are glycerides with 2 fatty acid chains, and you can modify diglycerides with a phosphate head to create a phospholipid, and that's what we're looking at here. So we see that it's a diglyceride because it has 2 fatty acid chains. This here is a saturated fatty acid, and this is a cis-unsaturated fatty acid, and they are linked to a glycerol, so 1, 2, 3, and so this right here would be our diglyceride, our plain diglyceride, but it has been modified here with a phosphate head, and we can see that in this phosphate head, we've got these 4 oxygen bullying this phosphorus with their high electronegativity to take electrons and force it to share kind of more than it would normally share with other atoms. And as a consequence, we have a negative charge. This is a phosphate ion, PO4 negative. And so we have this hard negative charge here. And there's another attachment up here. We've got this nitrogen group here that has another positive charge. So this area has charges. So it has hard charges here. But in addition to that, these are polar covalent bonds, so there's regions of partial charge. So this is a very charged area. So this is a very polar region of this molecule. But down here we have these fatty acid tails. They're lipids, so they are nonpolar. And so we have a special molecule. These phospholipids are amphipathic. That means they are dual-natured. They are both polar and nonpolar, and that gives them some special qualities. If you look over here, this is sort of a cartoon version of a phospholipid. We have the phosphate head here, which is polar, and then we have the fatty acid tails here, which are nonpolar. Well, when multiple phospholipids come together, they're kind of attracted to each other in a specific way. The polar heads are attracted to each other, and those polar heads are also attracted to water. So when we have multiple layers of phospholipids, they organize themselves in a particular way, and that particular way forms our cell membrane. So we have the polar heads attracted to each other, and then we have all this water out here in the cellular environment, and that arranges the phospholipid tails away from the water because they are nonpolar, they're hydrophobic, and then on the other side you have the same thing happening. So this forms a phospholipid bilayer. The amphipathic phospholipids form a bilayer, and that bilayer has this barrier, which is a hydrophobic region that keeps our cells together. It is really interesting and important to note that there are no hard connections between the phosphate heads of other phospholipids and the phosphate tails of other phospholipids. So the barrier of our cells is not a tough connection with each other. That means that these phospholipids are free to move and kind of flow, and our cells act more like waves in the ocean than they do a hard barrier like the walls of a house. And that's really interesting. So let's review. Glycerides are fatty acids linked to a glycerol, and a glycerol is a 3-carbon molecule.
There can be monoglycerides, which have one fatty acid connected to the glycerol. Triglycerides, which have 3 fatty acids connected to the glycerol, and they are the most common fat storage molecule for long-term energy storage, rather. Diglycerides have 2 fatty acids, and they can be modified with a phosphate head. Once you've modified the diglycerides, they become phospholipids, and phospholipids are amphipathic. They have both polar and nonpolar regions, and that is because the phosphate head is very polar because it has charges, and the fatty acid tails are not polar. They are regular old lipids. Now, these automatically arrange themselves in a bilayer, so they start forming with the tails hidden on the inside and the polar heads on the outside, and they are not connected to each other at all, and that bilayer forms our fluid cell membrane. And that is why glycerides are important and how our cells use fatty acids. I hope this helps. Struggle well.